Section 3.4 is going to go a little bit further down the rabbit hole of derivatives. We're going to talk about concavity and the second derivative test. You have talked about concavity probably before. Do you remember where you might have heard it outside of a calculus environment if you've already had calculus? Anatomy. Okay. I was thinking more along the lines of a math class. Does anybody think of a math class you've seen it before? You might have seen it in geometry. You might have talked about concave versus convex in geometry. Is that what you're thinking, Hunter? Yeah. Trig, you might have talked about it. When did you talk about it in trig? Do you remember? Okay. Yeah, you were talking about concavity with sine or cosine functions. You probably saw it one other place too. Probably saw it in an algebra course when you first were learning, or at least at some point were learning about parabolas. Talking where parabolas opened upward and they were concave up, or whether they opened downward and they were concave down. That's usually included in the material about parabolas. So we're going to talk in concavity in a little bit different sense this one. So go ahead and jot these definitions down, and I'll show you how that fits in with those ideas from algebra. For a function f that is differentiable on an interval, the graph of f is concave up if the derivative is increasing, and it's concave down if the derivative is decreasing. I want to draw two pictures of how a graph can increase, okay? So a graph can increase like this, or it could increase like this. Those are both increasing graphs, right? But they look very different. The first graph increases really fast at first. I mean, it's really steep. And then it sort of levels off, flattens out, right? This one is leveled off at the beginning, and it increases faster as you go. The slopes get more and more steep, right? This is climbing a mountain kind of thing, right? Eventually you're going on the side of it kind of deal. So what we're talking about with this one is if f prime is increasing, that's this graph. This graph is getting steeper. The derivative is getting steeper. Okay, both of these are increasing graphs, but this second graph has an increasing graph that's increasing faster as you go. The first graph still is increasing, but it is increasing less quickly as you go. It's flattening out. This graph right here, the first one, is called concave down because the slopes are getting flatter as you go. It's called concave down. The second graph is called concave up, and you can identify that the slopes are getting steeper as you go up. A lot of times you'll hear somebody describe this in an algebra context, especially with parabolas. This is a concave up graph, and this is a concave down graph, and the idea being if something can hold water. If it could hold water, it's concave up for a parabola. If it would dump the water out, it would be concave down. Now, on our graphs, they may not be full parabolas, so we don't want to have that full sense of it, because neither of these graphs that I started with are going to hold anything. I mean, right? They don't have that sort of other piece of the graph that would actually make them a container of some sort. But this still has, this concave up still has that same sloping feature that this one does over here. And this concave down graph still has this same sloping feature that part of this graph has over here. Now, that's all well and good, but where does the second derivative come into play? Well, this says that the graph is increasing, right? The derivative is increasing. How do you find where something's increasing? You take the derivative of that. What's the derivative of the derivative? The second derivative. So in order to find out where a derivative is increasing, we're going to look at where the second derivative is doing certain things. So in particular, if the second derivative is positive, then the graph is concave up. And if the second derivative is negative, then the graph is concave down. So there are some things here that are really important to be aware of. If a second derivative is positive, then it means the first derivative is increasing. And that's equivalent to concave up. If the second derivative is negative, it means that the first derivative was decreasing. And that is the same as being concave down. They're all equal statements about one another. It's kind of like on the last test when I asked you the question about the horizontal tangent line, and I said, if you have a horizontal tangent line, then you have f prime of x equal to 0 or something like that. And I said, they're the same statement. One's just sort of the notation, and the other one's the language. Same thing here. This is a notation, second derivative greater than 0. The language for what that means is it means that the first derivative is increasing. Or another piece of a language that it means is it means it's concave up. They're all language that mean the same thing. All right. As a result, sometimes graphs do not always fit into one of these sort of nice, neat, tidy boxes. They're kind of like the ones that Ben mentioned at the beginning from trig. Trig functions, if you take a look at sine or cosine, do this, right? And so they have some pieces where they're concave down, and they have some cases where they are concave up. Because they change concavity, the places where they change concavity have a name, and those are called inflection points. So an inflection point is simply a place where the concavity changes. That is, the graph changes from concave down to concave up, or vice versa. So this picture that I drew below, I'm going to just sort of identify for you what's going on in terms of where the concavity changes, or roughly so. These spots right here break it apart, at least visually. There's nothing precise about these values, but visually, they break apart a piece where it's concave up to where it's concave down, concave up, and then concave down, and then the last piece over there being concave up again. So those are the places where the inflection point would occur. So you might think then, well, how do I find the inflection point? Because we're going to finding the inflection points. Well, if this is concave up, what is the second derivative when the graph's concave up? It's positive. So this piece right here where it's concave up has a second derivative that's positive. The next piece right here is concave down, right? So this one should have a second derivative that is negative. Now, we learned back in chapter 1 with something called the intermediate value theorem that you can't simply go from positive to negative unless you equal 0. Right? That's what the intermediate value theorem said, which means this point right here, this inflection point, is the location where the second derivative equals 0. So we can find inflection points by finding a first derivative and then a second derivative and setting it equal to 0. It's the equivalent to finding a critical point, but you do it from the second derivative's equation instead of the first derivative's equation. All good? Okay, we're going to do one. Determine the intervals where the function is concave up, concave down, and then identify any inflection points. And we're starting out with a very basic polynomial. So you guys like these derivatives, so somebody tell me what the derivative of this is.
4x cubed minus 12x plus 2.
Now, if we were looking for increasing and decreasing and maxes and mins, we'd do something here, but we're not. We're talking about concavity, which means we need the second derivative. So what's the second derivative here?
12x squared minus 12.
Good. All right. So just like when we were looking where things are increasing or decreasing, we set this equal to 0. And we're doing it actually for two reasons here. One reason is because when we set this equal to 0 and solve it, we're going to get our inflection point, right? The other reason is because we're going to be able to draw a number line, and we're going to actually be able to look at what happens before and after on the number line to be able to decide where was it concave up and where was it concave down. So let's solve this. What do you got? All right, so we can do 12x squared equals 12, which is x squared equal 1. X is equal to plus or minus 1. You might have been able to tell that already from the beginning of this one. It's not a terribly complicated equation. But this has two possible inflection points that we're looking at now. And we need to figure out if, in fact, they do have those features. So again, number lines. So we're looking at a number line, -1, 1, and we're looking at test points, just like the test points in the last section. What are some test points that you might like to choose here? Okay, -2. 0. I love zeros, yeah. And 2. Okay. What are we going to test them in? The second derivative, exactly. And we're going to test them in the second derivative because the second derivative is what tells us the information about concavity. The second derivative positive means it's concave up. The second derivative negative means it's concave down. So we're using them into the second derivative, which is right here. So we're going to test y double prime of -2, y double prime of 0, and y double prime of 2. All right, so I've got 12 times -2 squared minus 12. And again, I really don't care what the value is. I care whether it's positive or negative. So what is it? That value is positive. It's actually a positive 36, in case you were keeping track. How about the second one, y double prime of 0? Yeah, so I put the 0 in here, which zeroes it all out. And then I get that -12 there, so this one ends up being negative. All right, the next one then is at 2. And what happens? Yeah, it happens the same way that it did on the first one because it's squared and I get a positive. Now you have to be really careful and you have to be really aware of what you're looking at because we've done things now, we've got positives and negatives. What I don't want you to remember, what I don't want you to forget is which piece of information you were doing this for. This is all about the second derivative. Second derivatives talk about concavity. So if the second derivative says it's positive, positive means that we've got a graph that looks like this, right? So we have something that looks like these. They're concave up. It's positive. And the piece in between is concave down. So we're supposed to be listing a lot of information on this. First, let's talk about where it's concave up. It says interval. So on what interval is it concave up? Right. It's concave up before -1, which is -infinity to -1, and then after +1, so 1 to infinity. That's where it's concave up. The one between is actually down, so what would we write for that interval? -1 to 1. How about inflection point? Okay, that's a good question. Would it be -1 and 1? What do you mean? Like, how would you like me to write that?
I'm asking are those the inflection points?
What'd you say, Sam? Right, those are actually two x values, aren't they? So we actually have two inflection points here, one at +1 and one at -1. So this is where things get a little bit dicey in terms of our notation. This concave down information was an interval, but it actually is written the same way we write an ordered pair point, right? But I need to write down ordered pair points because this said to find the inflection points, which is an x-y pair. So an inflection point, I will have an inflection point at x equals -1 something, and at x equals +1 something. So we need to put the -1 and the +1 in where? The original equation. All right, so go back into this original equation, x to the 4th minus 6x squared plus 2x plus 3. Plug in the value -1. What do you get? Do you get 0? Okay? And then plug in the value positive 1.
You said original equation, right?
Original equation. You guys were plugging in -1, right? On that first one? That one was the positive one, that's what I was thinking. That's what I'd written down. This one, the positive one's value is 0. The negative one's value is actually what? -4. Yeah, that's correct. It was late last night when I wrote mine down, so I wasn't sure. All right, but that does match what I have. So we got that y value of -4, that y value of 0 by plugging it into the original equation. Those two pieces of information are the two pieces of information we were asked to find. The concavity, the intervals where it's concave up and intervals where it's concave down, and the inflection points. In this case, there's 2 inflection points. Any questions on that? Actually, you know what? Before we do this, let me see. I didn't do this beforehand, so this may not work well. Graph it. I just want you to put it in your calculator and look at it. Make sure that it matches what you think is happening here. So in terms of what I'm saying I'm seeing happening, I should be seeing a graph that looks something like this.
So we're graphing second derivative?
Nope, the original equation. You should see a graph that looks something like this blue one at the top. The peaks and valleys may not be in the same locations and stuff, but it should look something like a W. Did it work out? Sam, do you see it? Yeah? Okay. So does that match, right? We've got it concave down, concave up, and then concave up, and then concave down, and then concave up. Excellent. Okay. We actually have something called the second derivative test as well. You might be thinking, wasn't that what we did? Not exactly. We used the second derivative, but it wasn't the second derivative test. The second derivative test actually gives us another way to determine if something is a maximum or minimum value. So if we have a function whose derivative is 0, right, f of c equals 0 at a specific point c, we can do the number lines like we did back in section 3.3, right, where we actually tested points. We could actually use the second derivative as well to tell us whether it's a max or min. Because if the second derivative is negative, what does it mean? About concavity, what does it mean? It opens down. This is what the picture would look like if it was second derivative was negative. It would be concave down. Well, if it's concave down, it has a maximum value. And on the second one says that if this second derivative is positive, then you know that means that it's concave up. And if it's concave up, it looks something like this, and that one has a local minimum. This one's easy to get tripped up on because we keep tending to use this ideas of being positive and negative to mean up and down, and all of a sudden now we're talking about maxes and mins in a little different way. So you have to be a little bit careful. Remember, second derivative really tells you things about concavity. Concave down means you have a max. Concave up means you have a min. So let's do one. This one asks us to find all critical numbers and then use the second derivative test, no number lines this time, use the second derivative test to decide if we have a max or a min there. Now, there's 2 ways to do this derivative. Somebody suggest one of them. Quotient rule, and that's the one I don't want to use. What's an easier way to do this derivative? We could do a product rule. That would be even harder. We could bring them x to the top, which would turn it into a product rule. Again, harder. All right, let me show you. What if we simplify what we're starting with? No products, no chains, and no quotients. What? Look at that. Isn't that awesome? We actually saw something like this happen once before. We did it when we did the power rule the very first time. Some functions, this one actually simplifies this way because there's no addition and subtraction in the denominator. That's what's letting us do that. Okay. I like that because I can take that derivative pretty quick. How about you? What's the derivative of that new version of our function over here?
1 minus x to -2.
Okay, so 1, it'll end up being plus, right? Plus x to the -2 because we bring that -1 exponent down. Another version of that then would look like 1 plus 1 over x squared. Okay, what are we supposed to be doing with this derivative now?
Finding critical point.
Finding critical points. So what do we do for defining critical points at this juncture?
Set it equal to 0.
Set it equal to 0. Excellent. Now what? I wrote something down wrong. I think what I wrote down wrong is the original function. Yeah, let's fix that. It's like this isn't doing what I wanted it to do. All right. Change the original function, have a plus sign in it. That'll fix what I want. Okay. Yeah, so now it will be that negative that you wanted it to be, Blaine. Okay. All right, that'll do what I want. Typo in the original problem, sorry.
What was it then?
Because we would bring that -1 down, yeah. All right, so now we're going to find out where this is equal to 0. So what can we do?
Add the 1 over x squared to the other side.
Yeah. So what would x equal?
Plus or minus 1.
Plus or minus 1, actually, yeah. Is everybody good with that? And cross multiply, take a square root with a plus or minus 1. If you wanted to, you could actually have not moved that 1 over x squared. You could have found a common denominator and so forth as well. We do not need to find all the critical points on this, though, or all the critical numbers. Why not? Did you catch it back in that second derivative test? Over here on the second derivative test. Okay, you guys are looking at your paper anyway. Part of the definition up in the very front of your problem said, suppose that f double prime is continuous and f prime of c equals 0. So we only need to worry about the f prime of c equals 0 part. So we really are concerning ourselves only with where the derivative is equal to 0 on these points, not derivative doesn't exist. Okay, second derivative test won't help us with those cases. All right, so what are we going to do? How can we do this now? What does the second derivative test say I should be able to do? Find the second derivative and plug these numbers in. So that's what we're going to do. We're going to find the second derivative. So what is the second derivative? We can actually use this one right here as the location to sort of pull it from.
2 over x cubed.
So this would be 2x to the -3, which is 2 over x cubed. You bet. So that's our second derivative, and we're going to evaluate that second derivative at our 2 critical points. So the second derivative at -1 and the second derivative at +1. So we're going to put in 2 over negative (1) cubed and 2 over positive 1 cubed. Do I care what the number is? No. I actually care what the sign is. So what happens on the first one? It's negative. The second one? It's positive. Okay, what does second derivative actually really tell us?
It's concave up.
Where it's concave up and concave down. If it's negative, what is it? Concave down. If it's positive, it's concave up. So at x equal -1, where it's negative, the second derivative, do I have a maximum or a minimum? I have a maximum, right? This little picture up here in green here, shows sort of like, looks like a parabola opening downwards. That gives me a maximum. And down here, because I got a positive, there, it's going to show up here in a minute. There it is, that green parabola opening upward. I would have a minimum. Now, this says determine all local extrema. It doesn't actually say whether we have to write whether it's a point or not. If we wanted to do a point, we could find it though, right? We would take that 1 or the -1 and plug it back in the original equation. It doesn't say we have to, so we won't. So we have a local maximum at x equal what? -1 right here. And we have a local minimum at x equal positive 1. That's not too bad, right? As long as the derivative is not too difficult to take, this is a pretty efficient way of doing it. We don't have to do all the test points for it. That's kind of a nice feature. Okay. This is another one where we're going to sketch a graph. This is actually a function you guys saw in your homework in 3.2. We're going to do something different within a section. We're going to actually sketch a graph of it. It says determine all significant features by hand and sketch a graph. That sounds very, it just sounds so broad. Doesn't it sound broad? It sounds like, oh my goodness, what all would we consider a significant feature?
I like her adjective more.
You liked her adjective better. Awful. Okay. Well, some things that you might think of for significant feature is certainly some of the things we've been working on in class. So what are some significant features of a graph? Max and min. Yeah, so that's going to be critical point stuff.
Inflection points considering its sine and cosine.
Yeah, you would definitely think about doing something with an inflection point. We may or may not have to physically find it depending on how the graph works out, but that is a significant feature. You might also have in your mind that your x-intercepts, maybe potentially a y-intercept might be a helpful feature. On this particular graph, sine and cosine, the other thing to remember is that these graphs are periodic, right? So whatever we have happening in one period, it's just going to repeat itself in the next period of the function. Sine and cosine have what period of what?
0 to 2 pi.
Okay, so they have a period of 2 pi, which means from 0 to 2 pi is usually where we draw that, and recognize that whatever we had happening between 0 and 2 pi is just going to repeat itself again. So we're going to draw this graph only between 0 and 2 pi with the recognition that it's going to repeat that same picture again, okay? That's a helpful thing to know. Otherwise, you have to ask yourself, well, how far do I go? Right? Now, depending on what the function is, you might also have to identify asymptotes, right? That would be a significant feature. We don't have asymptotes for this one, but some of you on your homework will have that. And then some of the others may have other features. All right, so before we head out, let's at least get some derivatives of this thing going on. What's the derivative?
Cosine. For sure is cosine x negative sine.
Okay, good. So I'm working on the max min because that's the first thing you guys said. So there's my first derivative. What do I do with it? Set it equal to 0. And I can solve this one by splitting these guys on either side of the equation and asking myself, maybe from a unit circle perspective, where are sine and cosine exactly the same value? I'm going to tell Dr. Tucker that you guys learned so much. Yes, at pi over 4 and 5 pi over 4. Very good. Let's see. So those are our critical points, which means those are our potential points for being a maximum or minimum value, right? All right, let's do our second derivative, because that's the second derivative test we can use here. What is the second derivative of this?
Negative sine x minus cosine x.
Excellent. And we're going to use each of those critical points inside of this to decide, do I have a maximum or minimum? Sound good? Okay. So we're going to evaluate f double prime of pi fourths and f double prime of 5 pi fourths. So I have negative sine pi over 4 minus cosine of pi over 4. And then I have negative sine of 5 pi over 4 minus cosine of 5 pi over 4. All right, so what is the sine of pi over 4?
Root 2 over 2.
Root 2 over 2. And the cosine of pi over 4?
Root 2 over 2.
Root 2 over 2. And they're both now negative because they've got subtraction signs on both of them. So this is negative root 2 over 2 minus root 2 over 2. And if you simplify it, that's negative root 2 over 2. The important question, though, is it positive or negative? It's negative. A second derivative that's negative means what?
Maximum.
It's concave down, looks like that, means we have a maximum. So the value at pi over 4 is a maximum value. Let's do the other one real quick. 5 pi over 4, what's the sine of 5 pi over 4? negative square root 2 over 2, but there's a negative in front of this, right? So we're going to end up with a positive square root 2 over 2. What is the cosine of 5 pi over 4? Negative root 2 over 2 with a negative in front of it, so we have another positive. So this is actually square root 2, which is a positive number. So it is concave up. So it's a minimum. So we have a maximum. I'm going to write this down. We'll pick this up next time. We have a maximum at x equals pi fourths. And we have a minimum at x equals 5 pi over 4.